The other day, someone requested a video about the proof method of induction. There are a lot of different places in mathematics you can go and talk about proofs that use induction, and in my experience, it's kind of an obsession in computer science. I mean, mathematically, in the case where a direct proof is possible, all other things being equal, the direct proof would usually be preferred, but I have encountered quite a few computer science-oriented people that are solely aware of induction proofs and get kind of frazzled when they can't use induction. Anyhow, induction can be a bit unbelievable the first few times you work with it. I know I always had trouble feeling like I actually proved everything I needed to when I first learned about induction. So instead of jumping into those areas or complaining more about computer science, and possibly obscuring some of the details, we're going to stick to an introduction of the proof device. Induction in a mathematical sense can mean two different things. However, they're both logically equivalent proof devices. The most straightforward is the principle of mathematical induction, which says that given a sequence of statements, S of n, if you can prove the initial statement, S of 1, and if you can prove that for any arbitrary k, the kth statement, S of k, implies the kth plus 1th statement, S of k plus 1, then the statement S of n holds for all n. This set of conditions builds a chain. In particular, when these conditions hold, we know two things. One, the initial base case holds, and two, any case implies its successor case. So with one, we can start with the base case being true, and then with two, we know that the next case, or rather the second statement, will be true. And then since we know that the second statement is true, we can use two again to show that the third statement is true, and so forth. Continual use of 2 can show the truth of the statement S of n for any given n. Being that induction works with sequences of statements, the tool is not at all clear without an example if you haven't seen it before. And an example will help illustrate how one actually goes about an induction proof. Suppose that for this example you want to know what the sum of the first n natural numbers is, for any given n. Now, there is a bit of discovery that needs to be done here, but in discrete math, when working with something indexed by the natural numbers, for any can be a big hint that induction will eventually be required instead of a direct proof. Our sequence of statements is just equivalencies for each n. So when n is 1, the sum is 1, when n is 2, the sum is 3, when n is 3, the sum is 6, and when n is 4, the sum is 10, and so forth. After some fiddling, you may note that 1 is equal to 1 times 2 divided by 2, and similarly, 3 is 2 times 3 divided by 2, as 6 is 3 times 4 divided by 2, and you may suspect that the pattern here continues. This discovery gives us the sequence of statements that we can use induction with. In particular, it gives us a proposed answer to the question, what is the sum of the first n numbers? That is, the proposed answer is n times n plus 1 all divided by 2. And that yields the statement S of n is given by 1 plus 2 plus all the way up to plus n is equal to n times n plus 1 all over 2. Okay, so let's go ahead and prove the proposition. To satisfy the first condition of induction, we only need to show that the base case is true. That is, the statement S of 1 is true. We've already done this, but to be completely explicit, we can just plug in 1 into both sides of the equation proposed, and yield a left-hand side of 1 and a right-hand side of 1 times 2 divided by 2 is equal to 1, which is equal to the left-hand side. The next condition requires the assumption that the kth statement is true, and using that to show the k plus 1th statement is true. Since the kth statement is true, we know that the equality 1 plus 2 plus all the way up to plus k is equal to k times k plus 1 all over 2. Now we start to investigate the k plus 1th statement. It proposes the equality 1 plus 2 plus all the way up to plus k plus 1 is equal to the quantity k plus 1 times the quantity k plus 2 all over 2. Once again, we proceed with a left-hand side, right-hand side argument. First, note that we can break up the left-hand sum in the following way. Doing so, we can use the equality granted to us by the assumption that S of k is true. This yields the following. Getting a like denominator, we have k times the quantity k plus 1 plus 2 times the quantity k plus 1, and that all over 2, which with some factoring is equal to k plus 1 times k plus 2 all over 2. And this is the right-hand side. And so we have just shown that the left-hand side is equal to the right-hand side using S of k. And that's a key point. You actually have to use S of k to say that S of k implies S of k plus 1. If you don't, then you may be attempting to do something directly instead of with induction. Thus, we have fulfilled both conditions of the principle of mathematical induction. And so we have the truth of the chain of statements that answers our original question, what is the sum of the first n natural numbers for any n? The second thing that we may mean by induction is the principle of strong induction, where in the second condition, instead of assuming that the kth statement implies the k plus 1th statement, we assume that we need the first through the kth statement to show the k plus 1th statement. As I mentioned earlier, these two proof devices are actually logically equivalent. And it's a good thing to spend some time thinking about on your own to get a better understanding of what exactly the principle of mathematical induction and the principle of strong induction say and how they are useful. Mind you, there will be cases where it'll be more straightforward to use strong induction over the principle of mathematical induction and vice versa. With that, if you want more practice with induction, working with problems asking for the sum of the first n things in a sequence is usually a good idea. If you're interested, here are a few problems that fit into that realm of things that you might want to think about. Anyhow, that's all I have for you today. I hope you enjoyed this video. If you did, go ahead and subscribe for more mathematics videos, and there's more stuff over here. Once again, this video was based on a viewer request, so if you have any topics that you would like me to discuss, you can go ahead and leave those in the comments down below as well. As always, I am Nathan, this is Chalk, and I will see you next time.